at the Chennai Mathematical Institute. So he joined us after a long stint at the ICTP. Ramadas is a physicist, actually. He's a physicist, mathematical physicist, mathematician, all bundled into one. And today he will sort of take us through GIT. Yeah, Ramadas, the floor is yours.
Okay, thanks. So my familiarity with GIT comes from moduli theory. And so where you're mostly concerned with semi-stable points and the orbits of semi-stable orbits. And my understanding is that in GCT, you are really more concerned with the complement, the non-semi-stable orbits, which would be correspond to orbits in the nilpotent cone. But in a sort of modern perspective, it's useful to, even to understand the nilpotent cone, it's useful to understand notions of stability and semi-stability. And also, yeah, so in any case, this is what I know, and that's what I will. So I have a perspective on GIT, which comes from concentrating on the semi-stable points. And so I think my brief is to give you an introduction to GIT, and then a little bit about the applications of Morse theory, the moment map to classify classes of orbits of reductive groups. And I'll mostly follow a paper of Linda and Ness, which I wish I had paid attention to. Even I know about the existence of this paper from decades ago, but I wish I had paid more attention to it. It's really very beautifully written. Okay, so without further ado, let me begin. So today will be mostly, I'm going to set up the formalism of GIT, affine quotients, projective quotients, semi-stable points, and also the nilpotent cone. Okay, so we work with the category of algebraic groups acting algebraically, so on algebraic varieties. So even though I say variety, sometimes even if you start with what is a reduced variety, you might end up by natural processes with varieties with non-reduced structures. They are usually not called varieties, but we will continue to call them varieties. So we have algebraic. So we have a group which is algebraic acting on a variety which is algebraic, and the action is algebraic if it's given by a morphism of varieties. So it's a group action of an algebraic group on an algebraic variety, which is given by a morphism given by the arrow here of morphism of varieties. So that means that everything is given in terms of polynomial equations. The maps are given by polynomials. And so whenever you have a group acting on a set, you have the notion of a quotient. Set theoretically, quotient basically identifies orbits as one point. Every orbit is identified as one point. But in the algebraic context, there are different versions of quotients, and you might not be able to give any structure of a variety to the space of orbits. So you may do with things which are weaker versions of this. So let me describe the versions that exist. So if I have a group, algebraic group acting on a variety like this, then we look for a morphism from x to y satisfying pi gx is equal to pi x. And what are the possibilities that can occur? So y is a variety always, and pi is a morphism. So ideally, you would like that the points of Y correspond to group orbits. So every point of Y corresponds to precisely one orbit of the group. And this is called a geometric quotient. So usually you're not able to get a quotient of this kind, though there are some important cases, which I will cover very quickly, where in fact this happens. What you might hope is that you have a variety Y with a map which satisfies this equivariance, pi gx equal to pi x, which is universal for such maps. In other words, given any pi tilde to some variety z, which satisfies this, it factors. So through this dotted map. So here, when I write the dotted map, I mean
water, 2 glasses of water, please.
Sorry. Did you say something?
I think Kevi's sound was on, and I just muted him.
Okay.
You can continue.
In algebraic geometry, when you write a dotted map, that means something special. It means a map that's defined outside a subset of smaller dimension. But here, I mean a dotted map in the usual sense. So there exists a unique such maps as that pi tilde factors. Okay, so let me there exists unique eta such that pi tilde is pi composed with eta. So this is such a pi is called a categorical quotient. And often you want stronger properties than that. And in fact, in the geometric invariant theory situation, the quotients that you get will have, stronger properties than the categorical quotient. So, so that will be what's called a good quotient. Good quotient, which is a whole host of good properties, which I will not list, which are just short of having a geometric quotient. So a good quotient is a categorical quotient. Pi is surjective. Then, most importantly, if I take for every open set affine open in Y, the functions on U are precisely the functions on pi inverse of U, which are invariant under the action of the group. So in particular, the functions on Y are just invariant functions on X. So, so a good quotient is a quotient that has this property, this property, and a bunch of others, which I will not list. Now, geometric invariant theory produces quotients which are of this kind. They are very rarely of this kind, but that is the case in some important cases. But usually this is what you can get, but this is a lot already. This is if you get this situation, you're already in good shape. Okay, so now let us start with some important examples of quotients which are very familiar, and they are in fact geometric quotients. As I said, this is not the typical quotient that you encounter in geometric invariant theory, but these are quotients that at least the first of the two examples you'll be familiar with, and it's really important for us. Both examples are important for us going forward. So two important cases of geometric quotients. So you notice, by the way, that when I say variety X, I have not specified whether these are affine varieties, projective varieties. In fact, so far, let's work in some generality. These are quasi-projective varieties, which means a projective variety or an open subset thereof. Okay. Very good. So here are two important cases of geometric quotient. Let V be finite dimensional vector space. Oh, by the way, I should have said this at the very beginning. We will be working with varieties over C. These are complex varieties. So let V be a finite dimensional complex vector space. Remove the origin of V. Then every non-zero vector, there is a unique line, one-dimensional subspace defined by a non-zero vector. So if I look at this set of one-dimensional subspaces, there is a map that associates to every non-zero vector, the one-dimensional vector space spanned by it. And this is the well-known projective space associated to a vector space, the set of one-dimensional vector subspaces. It is a natural structure of a algebraic variety, and almost by definition, it is a projective variety. And so when do two vectors give you the same one-dimensional subspace? If and only if one is related to the other by multiplication by a non-zero scalar. So this is actually a quotient by C star, and this is in geometric quotient. Okay, so here is your first sort of canonical God-given example of a geometric quotient. The projective space associated to a vector space is a geometric quotient of the quasi-projective variety got by removing the origin from the vector space and quotienting out by the free action of C star on what remains. Now there is a twisted version of this called, so supposing V is a direct sum of subspaces, say R of them, and let's give each subspace a weight, which is a positive integer. Let's assume that these are ordered like this. So this is greater than 0, and these are integers. And then you can let C star act on this by T acting on V1, VR is T to the D1, V1, T to the D2, V2, T to the DR, VR. So T is an element of C star. It acts on a vector in this direct sum. So each vector in the direct sum is given by its components in these subspaces, and a non-zero complex number acts on this R tuple in this manner. Then you can take
so Ramadas,
yeah.
Sorry, Ramadas, the DIs are some integers. That's all that is specified.
DI are non-negative, positive integers.
Positive integers. Okay. Yeah.
Yeah. Yeah. So then you can take, again, you can just identify vectors according to this, and you get, again, in fact, it is a projective variety. So this is called the weighted projective space. So warning, this is in general non-singular, singular. Okay, so these are both geometric quotients. In other words, each point of the quotient variety corresponds to precisely one orbit of the group, and the group in question is in both cases the algebraic group C star. Okay, now let us consider more general groups and more general actions, but not arbitrary kinds of groups. We'll be considering groups which are called reductive groups. So I will not give the definition of reductive. To have a definition that works in all characteristics is not straightforward, but I'll just give a list. So simple Lie groups are reductive. Then C star is reductive. Finite groups are reductive. And products are reductive. Finite products. And you can go modulo finite normal subgroups. So that's a list of all reductive groups. Take a bunch of simple groups, take a bunch of C star, take a bunch of finite groups, take the product. And if you can find a finite group that sits as a normal subgroup in the product, you take the quotient. Now, reductive groups are linearly reductive. So this this implication fails in positive characteristic, then leads to a lot of interesting math. But this makes life really much easier for those who want to do GIT in finite dimension over C. So what is linearly reductive? This means that every representation, every finite dimensional rational, so I should define a representation. Okay, I will do that in a minute. Every representation is fully reducible. So what is a representation? It's an action on a vector space. A linear action. So G is an algebraic group. V is any vector space is an algebraic variety. So you already know what an algebraic action of an algebraic group on a variety is. So that is an action. It's a linear action if it preserves the vector space structure, namely addition of vectors, multiplication by scalars. And what is fully reducible? If there is a subspace which is invariant under the action of the group, there is a supplement to the supplementary subspace which is also invariant. That may not be unique, but it exists. So, so this means that every representation can be broken up into direct sums of irreducible representations. And so in a more slightly sophisticated way, you say that every exact sequence of representations splits. So that means, so supposing I have a vector space V on which the group acts, and I have a subspace W on which is invariant, then there is a projection P from V to W, which is G equivariant. And so that is 1. 2, if I have V to W prime is a surjective map of G vector spaces, then there is a G equivariant splitting of this map. So here is how here is an example of how I'm going to give you a sneak preview of how these properties used. Okay. So how is this property used? So supposing I have a reductive group acting on a on some variety X, reductive variety. Then G also acts on the functions on X, algebraic functions on X. Now, this is not finite dimensional in general, but because the action is algebraic, this is essentially finite dimensional in a way that I make precise, try to make precise in the notes. This is part of the yoga of algebraic groups acting on varieties. That essentially means if I take any algebraic function, and if I look at all its translates by the action of the group, that is contained in a finite dimensional space of functions. Okay. So by the way, how I suppose it's clear to you how an action of a group on a set induces an action on functions on that set. So basically G acting on, so if F is a function, then Fg X is F of G inverse of X. Yeah. Okay. So now, so here is a sneak preview of how linear reductivity is used. So supposing I have G acting on a variety X and Y is a subvariety, okay, of X. Okay. So now because Y, so this is a closed subvariety. So everything is affine. Now let's assume everything is affine. Then in an affine variety, you have a closed subvariety is given by this surjective map from C of X to C of Y, the restriction map. Now, within here, I have the invariant functions, and within this, I have the invariant functions G. So linear reductivity will ensure that if I take an invariant function on a closed subvariety, there is an invariant function in the ambient variety that restricts to this. So invariant functions on closed subvarieties can be extended to an invariant function on the ambient variety, provided the group acting is linearly reductive. So this is a typical way in which linear reductivity gets used in the theory. Okay. Now, we come to the sort of the standard situation. You have G acting on a vector space, always finite dimensional.
Just a minute. Huh?
Yeah.
Yeah. So this second map, is it surjective?
That is the point. Linear reductivity ensures that.
So the second, if first map is that is surjective because of inclusion, so second map is also surjective by linear reductivity.
By linear reductivity. Yeah.
Okay. Thank you.
So since you asked that question, this is one of the situations where in positive characteristic you get into trouble because reductive groups are very rarely linearly reductive. So you could have a G invariant subvariety and a G invariant function on the subvariety, which does not necessarily lift to a G invariant function on the ambient variety. But that is just parenthetical. Very good. So now I'm going to launch into the main situation, the basic construction of GIT, which is when a linearly reductive group acts on a vector space. So now I will be stating the main theorems here, and then I will quickly go on to talking about the projective quotient and semi-stable points and the null cone. So this is a good opportunity for me to stop and ask if there are questions. I think you have seen much of this before, so which is why I've gone a bit fast.
So I think the only terminology difference is you call it nilpotent cone. People have used the word null cone so far. That is the only.
Yes. Yeah.
I think
okay.
that.
Yeah. I think.
Otherwise, I think it has been perfect.
I should use the null cone. Yeah. Yeah. Okay. Very good. So now, I have a linearly reductive group acting and a representation of G on a vector space. It's acting algebraically and linearly. Right. So now take the ring R of functions on V, polynomial functions. Now this consists of the constants plus polynomials of homogeneous polynomials of degree 1 plus direct sum homogeneous polynomials of degree 2, etc. In other words, the ring of polynomial functions on a vector space is a graded ring, graded by the degree of the homogeneous polynomial, right? And within R, so as I said, given an action of a group on a vector space, the same group acts on the functions on the vector space. F GF goes to FG, which is the function whose value at X is F, the value of F at G inverse of X. The G inverse is put here to make this also a left action. Okay. So now you can look at functions which are invariant under the group action. So RG is the subring consists of functions F, such that Fg is equal to F for all G and G. And so the basic observation is that this is also great. So Rg is R0, because constants are invariant, obviously, plus R1, R1G, direct sum R2G, etc. So why is that? Because the group action is linear. If you take a polynomial of homogeneous polynomial of degree D, it gets transformed into a homogeneous polynomial of degree D. So the group acts independently on each of these homogeneous, on the space of homogeneous polynomials of different degrees. So if I have an invariant polynomial of which is not of homogeneous of some degree, each of its homogeneous components will independently be invariant. So the invariant polynomial, invariant ring is also graded. Okay, in other words, yeah. I won't belabor the point. So now look at the ideal here of polynomials, invariant polynomials of strictly positive degree. So in other words, this consists of F such that Fg equal to F and F of 0 is 0. So these are just, this is the ideal of invariant polynomials which vanish at the origin. Okay, this is the definition. This is the ideal in Rg, but note that it's not an ideal in R. So let I be the ideal in R generated by this guy. Okay, this is the ideal in R generated by all invariant polynomials vanishing at 0. In other words, of strictly positive with 0 constant term. Very good. So now this is an ideal, and this is certainly not equal to R. Therefore, it defines a subvariety. So N is the subvariety in V, defined by I. So in other words, this consists of points of V such that f of x is 0 for every f which is G which is no, that's not correct. Let me not say it in words and make a mistake. For every f in I. So this is a closed subvariety in V in general. I mean, it's in general, it's a proper subvariety. In very rare cases, it can be all of V. Okay. So this is the nilpotent or null cone, sorry, that you heard about. So note that so far I have not really used that G is linearly reductive. I could have defined all this for an arbitrary group acting on an arbitrary vector space. So the null cone can be defined always. Now, what happens if G is what happens if G is linearly reductive? Well, okay. Again, I shouldn't. I can wait a bit.
So, Ramadas,
Yeah.
when you say so N is a subvariety defined by I, so
Yeah.
of course all these G invariant polynomials are all there, and so clearly, if I take any point in N,
Right.
it is 0 at all these invariant points. But you are so why did you sort of hesitate when you were trying to say that? I'm a bit confused.
No, you know, it is defined by the vanishing of all invariant polynomials. It is correct.
Of all invariant. Right.
Yeah.
Okay.
Yeah.
But it may not be a radical, is it? Is that the issue? Or it will always be?
No, but I was not. It need not be a radical ideal. Then the nilpotent cone need not be reduced. But that is not.
Okay.
That is not the reason I hesitated. I don't know why I hesitated. Okay. Yeah. Sorry. N is indeed defined by the vanishing of all invariant polynomials. It is a set of points.
Yeah. Thanks.
I mean, here. Yeah. Very good. Now, by the Hilbert basis theorem, there exist finitely many invariant polynomials that generate I. And in fact, if finitely many invariant polynomials generate I, you can take their homogeneous components and they will also generate I. So I can even say finitely many invariant homogeneous polynomials. Yeah, that generate I. So far we don't use linear reductivity. Now, if G is linearly reductive, so let me call these P1 to Pn. R is C, Rg. So this is the key result. So let me repeat. So let's start here. I have some arbitrary group. So let me just take that. Some arbitrary group, G algebraic group acting on a finite dimensional vector space. I take the ring of functions on that finite dimensional vector space. look at the ring of invariance, look at the ideal generated by the ring of invariance in R. Now, the Hilbert basis theorem says that because R is Noetherian, R is polynomials, algebraic functions on a vector space. So it's a ring of polynomials in finitely many variables. So it's Noetherian, and Hilbert basis theorem says that, Hilbert basis theorem says that R is Noetherian. That, what does that mean? That means every ideal is finitely generated. So by any set, so if I take more specifically, if I have a set S of that generates an ideal, I can find finitely many elements in that set that generate that ideal. So since the ideal I is generated by the set of all invariant polynomials of positive degree, there exists finitely many invariant polynomials of positive degree, which you can take to be homogeneous of positive degree, which generate I. Okay, so just list them P1 to Pn, where capital N need not be unique because the set of generators depends on how you choose it. But there exists a finite set of homogeneous polynomials that generates the ideal I. Now, so far in total generality, but the point is now, if G is linearly reductive, these homogeneous invariant polynomials that generate I actually generate the invariant ring as an algebra over C. In other words, every invariant polynomial function on the vector space is some polynomial expression with in capital N variables, where you plug in for each of the variables the corresponding Pi. Okay, in other words, let me spell this out. In other words, given any invariant function f on V, there exists a polynomial Pf, not uniquely determined, Pf in variables y1 to yn, such that f of x1 of x in V is equal to Pf of P1x Pnx. So this is the statement you have to understand. So this is what the finite generation of invariants amounts to. Is this clear? To say that the invariant ring is generated by certain invariant polynomial expressions P1 to Pn means that given any polynomial, any function, algebraic function on the vector space V, its value at a point is given by substituting the values of P1x to Pnx in the polynomial expression Pf, where, so to every f, there exists a capital Pf, which need not be unique, by the way.
Yeah. Nice.
Okay. So what does this mean geometrically? So geometrically, so we say, so in other words, the invariant ring Rg is finitely generated. So I'm talking in more abstract terms. So there exists an algebraic variety corresponding to it. So this dictionary you have possibly already seen, the dictionary between finitely generated C algebras and algebraic varieties. So it's a contravariant association. If you have a map of varieties going the other way, the map at the level of functions goes in the opposite direction. Okay, so R sitting inside RG sitting inside RG corresponds to a map from V to another variety, affine variety, whose ring of functions is RG, and that affine variety is usually noted by V mod G. So we have this map pi from V to, so RG is C of G, and R is C of V. Okay, so now let me say a bunch of stuff. Pi is a good quotient. So in particular, pi is surjective. Invariant functions on any open set are invariant functions on the inverse image. Blah, blah, blah. And pi inverse, yeah. So now, yeah. Now V mod G corresponds to a RG. Remember, R is R0 direct sum R1, etc. And this is equal to R0 plus R1G, etc. So this is also graded. So since RG is graded, there is an action of C star on V mod G. Also, if I look at RG, within this I have RG strictly bigger than 0, and the quotient is just R0, which is C. So in other words, if I take homogeneous invariant polynomials of which vanish at the origin above, they form an ideal in RG whose quotient is the complex numbers. So they define a point in V mod G, and that is which we'll call the vertex of V mod G. And that is fixed by this action of C star on V mod G. And pi inverse of the vertex is precisely the nilpotent cone. So this is, I mean, I'm using a lot of standard dictionaries here, which I don't have time to justify, but I hope this is, so what you should, let me just repeat this, because this is where all the geometry is. So let us summarize. So I have G acting on a vector space, reductive. I take the ring of functions on the vector space, which I call R. I take the ring of invariant functions, which is RG. This corresponds to an affine variety, which I call V mod G. This inclusion corresponds to a map in the other direction of morphism of varieties, V mod G. Within here, I have a distinguished point, which I call the vertex. Defined, so any point on an affine variety is defined by all the functions that vanish there. And here, the functions that vanish here are precisely the invariant polynomials of strictly positive degrees. And if I take the inverse image of these guys under pi, that's precisely the nilpotent cone, the null cone. Okay. N is pi inverse of mu. Okay, so this dictionary, I don't have time to justify. It is a matter of just piecing together this contravariant association between algebraic varieties and functions on them. And if you do that carefully, this picture will be clear to you. Okay. Now, so the key point so far is that and again, I made this claim without justification. I don't have time to do it, that pi is a good quotient. Very good. Now I'm going to consider projective quotients, and that is where semi-stable points and such things will come. So again, this is a good opportunity to pause for questions.
Yeah. So Ramadas, can I briefly ask you to say, because Raghavan did talk about, I mean, if you feel there is time, Raghavan did talk about conjugation of matrices. So here, and he spoke about going down to the quotient just being given by tuples of eigenvalues.
The example of GLN or SLN acting on matrices by conjugation.
Matrices by conjugation. So here, maybe if you can just sort of just.
Okay, I was going to do that. Okay, why don't?
Okay, good.
I was going to do that.
You can do it later whenever. Yeah, you can do it later also. I just thought maybe at that point this vertex and so on will probably get fixed. That's all. No, we can do it later also. I mean, I just thought. Hello.
Yeah. Was there some other question?
Can you just recall the definition of vertex once again, please?
Yeah. So the vertex one simple definition is I take the origin of V and take its image. Okay. Except it is the you take the since you were dealing just do that. Just take the origin of V and take its image under pi.
Okay. And algebraically it means just a point corresponding to RGR, ideal RGR.
No, not RGR. That is, see, RGR would be an ideal upstairs, ideal in R. So it will define a subvariety of V.
Okay. So
and
RG.
It is not RGR, it is RG positive R.
Correct. Okay.
The ideal that defines the null cone, you take the invariant functions vanishing at the origin above, and take the ideal generated by that. So so since we don't want to get lost in the thicket of notation, R consists of all polynomial functions on the vector space V. RG consists of invariant polynomial functions. Remember that constants are always invariant. Okay, yes. They're kind of non-interesting. But now if I take polynomial functions with no constant term, in other words, these are the polynomial functions that vanish at the origin of V, right? You can look at such guys and you can look at invariant polynomial functions on V of this kind, which vanish at the origin.
Yes.
Okay.
Yes.
So this is what I call RG greater than 0.
Okay.
RG is all invariant polynomial functions. RG greater than 0 is invariant polynomial functions vanishing at the origin of V.
Okay.
And now if an invariant polynomial function vanishes, there might be other points of V where all such invariant polynomial functions vanish. And this corresponds to points on the null cone.
Okay.
Yeah. Now, on the other hand, V mod G is defined by just invariant polynomial functions. Okay. So within invariant polynomial functions, there are the invariant polynomial functions that vanish at the origin above. Those are the invariant polynomial functions with no constant term. So if I take invariant polynomial functions and go modulo the invariant polynomial functions with no constant term, the quotient ring is just C.
Yes.
So in other words, invariant polynomial functions with no constant term are a maximal ideal in all invariant polynomial functions. Therefore, they define a point in the variety that I'm calling V double stroke G. This point is what I call the vertex.
Okay, yes.
Now, the inverse image of the vertex, so you can now, small exercise, the vertex is the image of the origin of V. And the inverse image of the vertex is precisely what I call the null cone. Now, all this is, I've been speaking a little set theoretically. If you want to talk in ideal theoretical terms, you should really, when you take images and inverse images, you should take scheme theoretic images and scheme theoretic inverse images, etc., to be entirely correct.
Okay.
Okay.
Yeah.
So KV, I think it's best that I relegate the examples to the notes and then come back to them in the next lecture. That will give me also an opportunity to warm up.
Okay, sure.
Because I do want to get to projective quotients today. I'm already, so I think I have now about 20, 25, 23 minutes left.
Yeah.
Okay.
Sure.
Very good. So now let's come to projective quotients. Okay. So now the key, so I already touched on this fact. So in this situation, when I have G acting on linearly on a vector space, we noted that so I have R and I have RG. This is graded, and this is also graded. And this corresponds to functions on B, and this corresponds to functions on what I call VWG. Okay. So whenever I have an affine variety defined by a graded ring like this, there is an action of C star on the variety. See, in the case of, in other words, to understand this, let's go back to the vector space V itself. And of course, in the case of vector space, of course, there's an action of scalars on the vector space. And in particular, there's an action of C star on the vector space. But if I didn't know this, I could reconstruct the action of C star by the fact that the functions on the vector space are graded in this fashion by R0 constants, homogeneous polynomials of degree 1, homogeneous polynomials of degree 2, etc. After all, the action of C star on B, so if T acts on B by multiplication by T, it acts on constants by T to the 0, it acts on linear homogeneous polynomials by T to the 1, and degree D by T to the D, right? Now I can define an action of C star on RG by exactly the same degrees, T to the 0, T to the 1, etc. And that will induce, this action on functions will induce action on V mod G, which is, in fact, it commutes with the action with pi. So I have pi, the quotient map from V mod G, V to V mod G, and there is an action of C star by scaling here, and this action of C star by scaling on V mod G corresponding to this. And in fact, pi of TV is T of pi V, where this dot product, so this induces this kind of dot action on points of V mod G. Okay. So T y goes to T dot y in V mod G. So let me repeat. So on on V itself, the scalar multiplication by T induces a function, an action of C star on polynomials, such that homogeneous polynomials of degree D are multiplied by T to the D. And the scalar action on V can be reconstructed by the action on functions. Now, the action on functions here gives this action on functions here on the invariant polynomials, and that in turn gets an action on V mod G, which I denote by this thickened dot here. So take a scalar T and a point y in V mod G that goes to T dot B in a particular way, in such a way that as far as the quotient map is concerned, it commutes with the C star action. Okay, so once we know this, we are good to go, because we know if I take V, I have V mod G, I have this map. On the other hand, if I remove V mod 0, I have this map to the projective space of V, T star quotient. And this is in fact a geometric quotient that we encountered. And this is a good G quotient. Now, if I remove the vertex from here, I have a T star quotient, which I will just denote this by PV. Okay, I will not, yeah, sorry. So this is just definition. At the moment, this is the definition, okay? Very good. Now, if you've been paying attention, you will find there is something wrong with this, what I have written here. So this is okay. To define the projective space, I must remove the origin and go to the T star quotient. And here, if I remove the vertex, and I can certainly, then there is an action of T star, I can take the quotient, this quotient is sort of related to the weighted projective space that I talked about earlier. So there is no problem here, but the problem lies here, because it is not true that V minus 0 maps to V mod G minus the vertex, because what is the inverse image of the vertex? It is the nilpotent cone. So to make this correct, I'll have to remove this
V minus null cone
and remove the null cone. And now, because I'm not taking the quotient of V minus the origin by T star, I don't get all of the projective space. I get PV minus the projectivized null cone. Now we are in good shape. This is a T star quotient. This is a G quotient. And by the fact that this is a categorical quotient means that there will be a map like this. And in fact, there's a commutative diagram like this. So let me call this pi. Let me call this pi P, P for projective. And so we have, therefore, this situation. Let me summarize. when I have a reductive group acting linearly on a vector space, if I remove from the projective space of the vector space, if I remove the points correspond to the null cone, then I get a map to a projective variety, which is G equivariant. And in fact, this is a good quotient. So, so we have now snuck in a closed subvariety of the projective space of V, which is the projectivized null cone, and we are now working with the complement of that closed subvariety, and this is precisely the open set of semi-stable points of PV for the action of G on PV. So let me summarize everything with a theorem. Let a reductive group G act linearly on a vector space V. Let PV minus PN be the open set of semi-stable points. So I'm defining semi-stable points as the complement of the projectivized null cone. We will come to a more intrinsic, a more explicit definition of those. Then there exists a good quotient by with the projective variety. Okay, so what is the sort of more? So I have defined a semi-stable point by what it is not. Can I define it in a way that gives it some positive description? So the point X in PV is semi-stable if there exists a homogeneous invariant polynomial P such that P of X hat is non-zero, where X hat is any point in V minus 0 above X. So what do I mean by above X? So so remember, you have V minus 0, you have this projection to PV. X is a point here. Any point, so X is a point of projective space is a one-dimensional subspace. A point above X is any point, any non-zero vector lying in that one-dimensional subspace. Okay, so note that a homogeneous polynomial is a function on V, so I cannot evaluate it at the point of projective space. But if I choose a point corresponding to that one-dimensional subspace, any non-zero vector, I can evaluate the polynomial there. And if it's non-vanishing at one of these points, then it will be non-vanishing at any non-zero scalar multiple of that point. So this is an invariant notion depending only on x. Okay, so the notion of semi-stable point is well defined. And this is if a point is semi-stable, clearly a neighborhood point in a neighborhood is also semi-stable. So the set of semi-stable points is open. And this is precisely the set of points which lie in the complement of the projectivized null cone. Again, by the nature of definition, this is an open, Zariski open subset of PV, which is invariant under the action of the reductive group. And the central theorem is that there is a good quotient of this open set by the reductive group, which is itself a projective variety. Okay, so now I want to tie up this. I want to say something explicit about how this projective variety is exhibited as a projective variety in terms of a set of generators of the invariant ring. But I think my audience must be somewhat saturated. So I think I should basically stop here and ask if there are questions. And in any case, what I plan to do in the next lecture is actually start with a quick review of what I said towards the end, exhibit how this variety is actually a projective variety. So this is where the weighted projective space construction will come in useful. And then give some examples, which will be hopefully illuminating. And then I have to go towards moment maps and such. KV?
Lovely. Yeah. So any, so that looks good. Yeah.